So functions of several variables has some slightly different behavior than functions of a single variable. So we'll concentrate on them. So what is an example of a function of a several variable? So several here always means more than one, because if you have a function of a single variable and a function of two variables, they are different. They behave totally differently. But a function of two variables and three variables, they behave the same. Okay, so that's how they behave. So we have these two sections. Last semester we did functions of a single variable. Now we'll have more variables. An example of a function of several variables, we always have such things. For example, volume of a cylinder. Okay, so cylinder is something like this, remember? Okay, so we have here radius and here we have height. Okay, so volume is pi r square h. Okay, so we have two variables here. The volume depends on these two values. So since we can change them, these are variables. Okay, so if you look at it this way, we see that functions of several variables are everywhere. We studied such things last semester, but we always gave a relation between R and H. For example, we said volume is fixed, so then R and H, they cannot be both free. One of them depends on the other, so there's always, last semester there was always one single variable. Okay, so in this semester when we are looking at these things, we will look at them as two independent variables. Okay, so generally we will be interested in two or three variables. Okay. Generally, in calculus, we consider only two or three variables. I'm writing this to make you happy, since we want to draw pictures. But the techniques we develop are more or less, at least the spirit of the techniques always hold for any number of variables. Okay? But if you go beyond three variables, you cannot draw a picture. And even with the three variables, sometimes we will not be able to draw a picture. So simple examples are polynomials. Are polynomials and rational functions. Okay, so for example, if you have x squared y plus y z cubed plus x y z, okay, plus 7. This is a function of three variables. Okay, or you can have x plus y over z minus y. Okay, so a polynomial over a polynomial, we have a rational function. So we will mostly be dealing with these things. The important concepts are domain and range. Domain is more important. Okay, so this is where the function makes sense. Okay, so for example, you see that this function makes sense when z minus y is different than 0. Okay, we have no condition on x. Okay, but as we did in the last semester, sometimes we have a story, and in that story, we construct a function. That function may be defined on a huge set, but for that function to be related to our problem, we must restrict the parameters. Only for certain values of the parameter, the function makes sense in our story. Okay, so then we don't take the domain as where the function makes sense, or a subset of it where the function relates to the problem in hand. Okay, so that's again something that we know from last semester. Now, one thing that the main thing that makes functions of several variables different is the point, is the direction you approach to a point. Okay, so we are doing calculus, so we'll be interested in limits, in derivatives. Why are we interested in limits? We are interested in derivatives. When you take the limit of a function, while the point is approaching to a fixed point, in one variable there are only two directions. Okay, so we mentioned this as right limit, left limit. Okay, so here there is no right and left, there is everywhere. Okay, so the main difference between one and several variables is in the direction of limits. Okay, so this thing does not occur in several variables. So one variable, we are on the real line, we have a fixed point p sub 0. You approach p sub 0 from this direction or from this direction. Okay, but say two variables, we are in the plane. Okay, so this is x, y coordinates. We have a point p sub 0. Now where do you approach it? Okay, so you can approach it like this. You can approach it like this. Okay, so this is also an approach. You can approach it like this. That was also the case here. In one-dimensional case, we could approach it like this. But again, your jumps are restricted. You either jump to the right side and come closer, or you are on this side and come closer. But here, you can also approach it like this. Okay, so you can do this a million times, 100,000 million times, okay, billions and billion times. That's we are talking about infinity. Eventually, we want this so that after a while, all the points are in a small ball. Okay, I take a smaller ball. Okay, maybe sometimes you jump outside the smaller ball, but then after a while, maybe a later while, again all the points will be inside. Okay, so that is what we should keep in mind. When a point is approaching to a point, just like in one-dimensional case, it is not steadily approaching here, but here we said that P approaches here means that I can take a small delta neighborhood around this, and I take any point here, and then I do whatever with this, with my epsilon stuff, etc. We will not do epsilon delta calculations. Epsilon delta calculations will not show up in the exam, but you have to understand how epsilon delta calculations work. Even if you don't do this, even if you think that you will have some difficulty in applying this, you should have no difficulty in understanding how it works, because that's the soul of limit. And limit is derivatives, and derivatives is calculus. Okay, so we are doing calculus. If you want to drive a car, you must understand that it runs on gasoline. Okay, so that's the stuff here. So when we say that instead of a delta neighborhood, when we say a delta neighborhood, it will be going to be a ball here. Okay, so for example, this part. So maybe I'll take this ball. So this, when I magnify it, it will look like this. So when I take this ball small and I take any point in this, it will be my delta neighborhood. Okay, so that's how we will approach limits in this case. But suddenly this tells you that there is no direction. Okay, so there is only affinity. A point is close to another point, but in which direction it is close, it doesn't matter. We cannot decide on that. Okay, so you see there is one concept here which showed up a million times in mathematics, so we gave it a name. So this part is a open ball. The word there is open. So what is open? Okay, so those things these technical descriptions will show up. So I want to give a short review, well, not review, but short description of these things. Neighborhoods of points will be used extensively, will be used in several variables. So what we want to do in a neighborhood is we want to be able to move around. We are taking limits, okay? So in one-dimensional case, there is this point. I want to be freely moving around this. So what do we say? We take an open neighborhood around the point, okay? So this part. So this is my point, P sub 0, and I have this A, B. I talk about the interval A, B. This is an open neighborhood of P. Okay, so we never described the technical term for open. We just said that if you remove the boundary points, it is open. Okay, so that's also true for several variables, but then in several variables, it is difficult to visualize what a boundary point is. But if you can visualize the boundary point, that's always the same concept. If you have a set, you remove the boundary points, if any, what remains is an open set. Okay, so that's what we are trying to make formal now. In 2 dimensions, we have this ball. Okay, so this radius is delta. So we talk about the set of all points in R2, okay, such that the distance between P and P sub 0 is strictly less than delta. Okay, so P should be chosen like this. If you choose P here, on the boundary, okay, we look at this thing. Nobody has any question about it. This is the boundary. The distance between a boundary point and the center is exactly delta. We are allowing that out. We don't want that. So this is an open ball of radius delta, positive of course, at P sub 0. So again, we have the word open. Okay, but this thing, this is denoted by, well, in different books it is denoted in a different way. Let's today denote it like this. There's no standard notation for this. Everybody, you tell that this notation is referring to a certain thing and you use this. The main idea here is that I'm going to take limits around this point. I can move in every direction around this. I can take my point in any way around this. Compare it to this one. Okay, so here I can move freely around P sub 0. So I'm now trying to make this concept clear. Okay, what is the other option? If this is P sub 0, and if I consider a set like this, okay, here I cannot move freely around P sub 0. I restricted myself only to this part, but there are also points here. I'm not considering them. Okay, so here we cannot move freely around P sub 0. Okay, so the whole concept of taking limits is that you should be free around that point, so that you can choose any point without any restriction. The only thing that will matter to us in calculation is that the point you choose is close in distance to the center point. Okay, so it looks like that we can make that clear using this concept. So the main definition in these things is an open set. Okay, I will not go into details because this is topology, and topology is a fascinating subject. We can do a whole semester on different definitions and how they are related to each other. But we'll only be interested in this open set. A set, say U in R3 or R4, or R3, R2, or R3, or actually in Rn, or in any Rn. I can choose the dimension freely because I'm using this notation. That's why we use this notation. Okay, now this notation is true in one dimension. There it represents absolute value. In higher dimensions, it represents distance. Okay, so it doesn't restrict any dimension. Here I can also put n. So a subset here is called open. Okay, so this is the formal definition. If for every point p sub 0 in U, okay, so let me draw a picture. So suppose this is something like this. This is U. I choose an arbitrary point. I should be able to repeat this result for every point here. Okay, so that's the strong thing here. For every point here, there is a radius. There is okay, we don't mention its radius. There is delta positive such that the ball of radius delta centered at p sub 0 totally lies in U. Okay, so that means around this I can find a ball like this of well, no arrow delta. So this ball totally lies inside the set. Okay, I choose another point. I can choose a point very close to the boundary. Here I'm not taking the boundary. Okay, so I didn't define the boundary, and probably we won't need a technical definition. But a boundary point is where you cannot do this. Okay. So for example, let us give our first example. Here we call this an open ball. Here, are we justified in calling it an open? Let's check that a ball is open. Example. An open ball BR P sub 0 is open. Okay, so I'll show this by picture. So this is our, okay, let's call this Q sub 0 so that I can use precisely the same notation here. Okay, so this is Q sub 0, the radius is R. Okay, take any point here. Can I find a small ball that totally lies in it? We can immediately see in the picture that we can do it. So what you are doing is you join it to the origin. So this is my P sub 0. You join it to the origin. You go up to the circumference. Then take half of this. Okay, take half of this as delta. Then you see that I have this ball. This ball now totally lies inside the big ball. Okay, so this is just to keep repeating to you that we need open balls in taking limits. Of course, there will be, maybe not in calculus, but in real life of an engineer and a scientist, there will be cases where your problem is such that approaching the point from certain directions does not make sense. So then you'll use restricted limits, but that's later. Okay, so this is what we want for openness. So I think we also need the word closed. Now the words open and closed in real life are opposite terms, but in mathematics they are not. Okay, a set can be neither open nor closed. So let's give a definition of closed. Basically, closed means that you take an open ball and then add all the boundary points. Okay, a set U is closed if its complement is open. Okay, so now to check whether a set is closed, by definition, you go to the outside of the set. If when you are outside the set, if you are always safely away from the set, if you can always find a small delta ball, an open ball around you, and the ball does not intersect the set, then you are safe. Okay, so if wherever you are in the complement of the set, you are safe in that sense, the set is closed. Okay, and technically, let me give the definition of a boundary. So technically, a boundary of a set, or rather the boundary of a set U, denoted by, almost always denoted like this. Okay, so partial derivative of U with respect to nothing. Okay, so that's generally the boundary, denoted like this, are the points such that every ball every ball around those points contain both a point in the set and a point in the complement. Okay, so that's the technical thing. What we are saying is that, okay, so suppose this is my set. We all want this thing, this point, to be a boundary point. So technically, how do we recognize it? Take any ball around this. Of course, the interesting thing is when you take small balls, because if you take a huge ball, it contains everything. But we are insisting that what we are going to say should hold for every ball. So the challenge is when you take smaller and smaller balls. If I take a small ball, you see that there is a point in the complement and there is a point in the set. So no matter how small you choose this ball, this will hold. But if you take a point here, if you take a large ball, okay, it contains a point inside the set and outside the set, but this should hold for every ball. Now I take a smaller ball. You see that now in this smaller ball there are no outside points, there are no complement points. So as our intuition tells, the definition fits. This point is not a boundary point, but these are boundary points. Okay? So we will be mostly interested in understanding open set. When closed set is required, I'll remind you how it behaves, but this is the concept that should show up in several variables. Okay, so another thing that we will talk about set is bounded set, but that's easy. A set U is called bounded. Okay, it is called bounded if it doesn't go to infinity. There are several ways of saying it. A nice way to say it is, of course, you can find elaborate definitions. You say take any 2 points on it, calculate the distance. Okay, so there must be a number so that this distance does not exceed that number. Obviously, that's a bounded set. But this is difficult to check. So we try to find a definition which will again give us the same bounded sets, but easy to check. The easiest distances to check are distances from the origin. Okay, so you look at the points in the set, you look at their lengths. This is the distance from the origin. That should be bounded. As a number set, that should be bounded. So how do we say this so that nobody understands it? It sounds scientific. We say that a set U is bounded if there is R positive such that U is totally contained in a ball of radius R at the origin. Okay? So every point in the ball of radius R has distance from the origin less than R. So this says that every point here has length less than R. Okay, this is easy to check. Obviously, whether a set is bounded or not bounded makes a difference on the set of functions defined on the set. That's why we are interested in these sets. Okay, if we do topology, then we'll be only interested in sets. As I said, it's a fascinating world. But in calculus, we'll use only these concepts because we are interested in the sets defined on these. We are interested in the functions defined on these sets. Okay, so how are we interested in that? So let me check what we are supposed to do. So we have a recipe to cover in every section. Okay, so let's give some easy examples because easy examples carry the idea. Then in a complicated example means that you have to apply the same idea but with more calculation. Okay, so for example, this should be, okay, so what is the domain examples? What is the domain of okay, so this is from the book f of x and y equal to square root, okay, so I kept instead of x plus y plus 1 divided by x minus 1. Okay, so you see the idea is simple. Here we'll find the set of all x, y so that inside the square root it will be non-negative, and x minus 1 should be non-zero. Okay? So first, we want the domain, before we do the calculation, is the set where x plus y plus 1 is 0 or positive, and x minus 1 is different than 0. Okay? So when in everyday language you say n, you'll intersect them. Okay, so let's first look at this one. So for such things, obviously first you look at x plus y plus 1 equals 0. So that is, what is it? Let's say y. It's always easier to visualize it like this, minus x minus 1. Okay, so it's a straight line with slope minus 1. So it is like this. But when x is 0, it passes from minus 1. So it is this line. Okay. So now we are interested on this line. Observe that on this line, this is 0. So we are interested when on one part of this where it is positive. So you just choose an arbitrary part, an arbitrary point where it is easy to calculate. I can choose the origin, x, y, 0 plus 1 positive. So this function is positive at this point. But this function is continuous. That's also we have to check. Okay, if this function is positive and if this function is continuous and it is positive here, it cannot be negative here. Because remember the intermediate value problem. Take any path from here to here. Along this path, you have a continuous function, okay, which takes a positive value here, negative value here. Somewhere in between, it must be negative. It must be 0, but it is 0 only here. Okay, so everything on this side, it is positive. So on this side, on this shaded part, x plus y plus 1 is positive. And also we have this part. So this is this part satisfies this condition. Then we look at this one. This is easy. So this is, so let's put the numbers. This is minus 1 here. And this is 1. We take out this vertical line on which x minus 1 is 0. Okay? And everything in the complement of this is included. All these parts are included. When we say and, we are intersecting those things. Their intersection is this part. Okay, so let's take this out. Now their intersection is this. This part minus this line. Okay, so that's the domain of this function. Okay, so the idea is similar in the other cases. So you see that in this setup, for example, this region is not open, okay, because I have boundary points here, okay, and this region is not closed, okay, because here these are also boundary points, but they are not included in the set. Okay, a set can be neither open nor closed. It's not like a window. Okay, so these are the easy concepts. Okay, so let's talk about graphs, because that is why in calculus we restrict our attention only to 2 or 3 variables, because we can draw pictures. Now if y equals f of x, now we have for this part we have the x coordinate and y is given here. Then for every point in the domain of this, I have a corresponding point. So I have a graph like this. Okay, so every point here is of the form x f of x. And the graph is a curve. Okay, next, suppose we have z equals f of xy. Then for this xy, I have this plane, xy plane. And for this z, I have the z-axis. Now for any point here, So suppose the function is defined everywhere. For every point here, I get a point on top. Okay, so what we are doing is just like here. So here, for example, suppose we had the region here. You take this straight line and bend it according to this rule, and you put it here. Okay, so that's the graph of a function. So here you do the same thing. You take this plane, according to this rule, you bend it, and you put it up here, and you get a surface. So suppose our surface is nice. It is something like this. Any point on the surface is of the form x, y, f of x, y. Okay. Now suppose we have w equals f of x, y, z. For this x, y, z, we have this. This is the domain, x, y, z. And for now, w must be perpendicular to this. So we don't know where w goes in 3 dimension. And this w is in the other dimension. Okay, so now if you have a function, what you do is you take this solid 3-dimensional space, you bend it according to this rule and move it into the 4th dimension, and nobody knows how to draw a picture of it. But the techniques we develop here, and in particular the techniques we develop here, will also explain us what is happening here without drawing it. And of course there are other dimensions where you see I cannot even draw the domain. In the next thing, suppose we have k equals f of x, y, z, w, then the domain is 4-dimensional space. I can't draw it. And the graph is in 5th dimension. Okay? But the techniques, we should derive such techniques here that they will tell us, applying those things blindly, algebraically, we should be able to derive conclusions about these functions. Okay, so that is calculus. Okay, so that is, let's draw one popular graph here, which we will use several times. Okay. We will be looking at the volume, etc., of the surface quite often. So one example is z equals 1 minus, or what is it? Okay, here it is 4 minus. So let's say 9 minus x squared minus y squared. Okay. So it is something like this. X, y, z. When x, y, z is 0, z is 9. Okay, so let's start from here. Okay, but you see that when x squared plus y squared is a fixed number, z is always the same number. But x squared plus y squared is a fixed number on a circle. So here I have a circle like this. So first of all, let me draw this, and then I can play on that. So this is going to be something like this. So suppose y is 0. You see that when y is 0, I am in the xz plane, and I have a parabola here. So this thing is going to be a parabola like this. And in the yz plane, it's going to be another parabola. Okay, so it is this surface we have. Now, when x squared plus y squared is fixed, I have a circle here. And on this circle, z is the same. Okay, so on top of this, so maybe it's here. Okay, the value of the z is the same. X, y changes, but z doesn't change. So we have names for these things. These are called contour lines. And these are called level curves. But these names are, again, not universal. From time to time, they change these names. Okay, so check what the name is given in the book. Okay, so you are not responsible to memorize the current name for it. Okay, so you have to understand the idea. Okay, so these contour lines and level curves, they are used in trying to draw the picture to get an understanding about the graph. Other than that, we will not have much use on that. I'm trying to follow the recipe. Okay. Okay, so there is, you see, I think the names change. Okay, so that's all for the beginning of this. Now let us start actually doing calculus. Now let's talk about limits of this. Okay, so what do we do with this function? So why are we interested in these functions, in these spaces and functions? Okay, so we will be interested in rates of change. So that is derivative, basically. In order to understand derivatives, in order to understand these, we need to understand, we need limits, concept of limits. Okay. Obviously, after you understand limits, apply it to derivatives, you get rules. Once you have rules, you are finished. Okay. Then you don't have to use limits all the time. You use limits only when these rules don't apply. Okay. You get some borderline cases where where the conditions do not fit to the rules, because every time you have a rule is a theorem. If you read the theorems in any math book, it says that under such and such conditions, the following holds. Okay, so if you just erase these conditions and you just said the theorem is saying that this holds, okay, you are in a big mistake, because under different conditions, something else will hold. How do you develop these theorems? You go down to basic, you go down to fundamentals. We have definition of limits, we have epsilon, deltas, open sets, closed sets, etc. Okay, it is difficult to reach conclusions from these, but certain results are always required. So we check whether those results hold or not. It turns out that those everyday results will hold under some mild conditions. So you have to obey those mild conditions. When those conditions do not hold, then you again go down and develop what you should do to get your result. You are looking for a number, for example. Okay, so in order to understand limits, we will do open sets, etc. But limits go in hand with hand continuous functions, continuity. Because remember, again, in one-dimensional case, in order to calculate a limit, if you use the definition, the formal definition, which I'll write in a minute, you have to guess correctly what the limit is, and then using epsilon delta argument, you must show that that limit is actually the limit, according to the definition. Okay? Since this, you cannot apply this all the time, we try to find methods for this. It turns out that there are functions whose limit you are trying to calculate at a point, but the function is nice, the function already takes the limit at that point. If you evaluate the function at that point, that's the limit. So why worry about epsilon delta stuff? The only thing to do here is to recognize which functions are continuous. Okay? So this is the underlying machine. We will spend some time here, because in 2 or 3 variables, this connection is more complicated, more interesting than in the one-dimensional case. In the one-dimensional case, in particular in the cases we looked at, there were not many singularities. Okay? Well, while you are approaching to a point, the graph either hits it or the graph goes away, and you can watch where it is going. Okay? Of course, in some cases it oscillates, but again, like sine 1 over x, you can draw a picture and you can understand what's happening there. But here, the graph is difficult to observe, and very unexpected things hold. So that's what we will do in this case, in several variables. So let me remind again what we mean by the definition. The formal definition of limit. So we are starting from here. That is the fundamental thing. Using limits, we will understand what's happening. Then the next question is, okay, these limits are too complicated to apply. Then we'll talk about continuity and we'll eventually go to derivatives. Okay, so we have a function, we say limit of a function of parameter p as p approaches p sub 0 is equal to a number L. Okay, so here L is a number. Okay, so this is a number. Okay, since we are doing calculus, this is a real number. Later on, when you do complex calculus, it's going to be a complex number, but whatever you are doing, it's a number. So f is a function. Okay, so p and p0, p0 are vectors in Rn. Okay, so here, when n is 1, we did this last semester. So in R2, 3, we can use the same notation. Okay, so we say that limit of this function as p approaches p sub 0 is L if the following holds. If the following epsilon delta argument holds. Okay, so as just like in the one-dimensional case, except that here we cannot draw a picture, we want these values to be close to these values. Okay, same story. What do you mean by close? Everybody has a different idea of close. So we call your idea of close epsilon. Okay, no matter which epsilon positive you come up with. Okay, so for any epsilon positive. So this is your decision that when two things are close enough, if their distance is less than epsilon. You can change this later on, but okay, so we call it epsilon. So you decide when you will call these two numbers close. Now, is it possible to arrange it by making these two things close? There exists, if the limit is this, there exists another measure of closeness, delta positive, such that whenever I choose p close to p sub 0 by this delta, whenever this holds, okay, let's read. Whenever p minus p sub 0 in absolute value is less than delta, then we please you. Okay, so this is what you are trying to understand, less than epsilon. Okay, so again, in one-dimensional case, we have here this thing. Okay, in one-dimensional case, so this is n equals 1. This is p sub 0. So this distance is delta. This distance is delta. You choose your p from here. So p is chosen from here. In two-dimensional case, so this is your p sub 0. This is your delta. So this is now n equals 2 case. You choose your point here. Okay, so that's it. That was the most crucial sentence, so I repeat it. You choose your p here. You see, we are not saying that you choose your p in a direction parallel to x-axis. You are not going to choose p along a curve. Okay, you are not going to choose p plus some condition. The only thing is that p is in this open ball. Okay, if I can find a small open ball so that wherever you evaluate the function, the value of the function is close to the limit. Okay, so close is, you decide how close it will be. You make this very, very small. If the limit is actually L, then I will find another small ball. Okay, but the interesting thing about small balls is, remember that wherever you stand in the ball, you still have elbow space from the boundary. Okay, an open ball is open. Okay, so that's how free the parameter is in calculating these. I repeat this because we will start doing examples, in which case, in order to calculate this L, we'll try to approach this along a straight line, because that's easy to calculate. Okay, and then we will discuss how much information it gives to us. Okay, so let's stop here, and next week I'll continue from there. We'll do actual calculations.